Welcome students. Today we are going to explore the topic chemistry of organic compounds, commonly known as organic chemistry. Organic chemistry is a field of science that is completely devoted to the study of carbon and its compounds. Now you might wonder why carbon is so important that a whole field of science is devoted to its name. Let me tell you in brief. If you look into the carbon atom, its atomic number is 6. It has 4 electrons in the last shell and its valency is 4. That is, it is tetracovalent. Since carbon's valency is 4, it can form bonds with 4 atoms of other monovalent elements. Namely, it can form 4 bonds with 4 hydrogen atoms and can form methane. It can also combine with 4 chlorine atoms, giving rise to carbon tetrachloride. Another unique property of carbon atom is that it can form covalent bonds with other carbon atoms, giving rise to large carbon molecules or large carbon compounds. And this property is known as catenation. Because of these properties, carbon can form millions of organic compounds. The food that we eat, the clothes that we wear, the cosmetics that we use, drugs, medicine, fuel, all of them has carbon as its constituent. Now you know why carbon is so important and the whole field of science is devoted to its name. In this lesson, we'll strictly focus on compounds formed between carbon and hydrogen. And the compounds that are formed by carbon and hydrogen only are called as or are known as hydrocarbons. Any organic compound can be considered to be a hydrocarbon or a compound derived from hydrocarbon. For example, if you take CH4, that is methane, it is a hydrocarbon. Whereas CCl4 is not a hydrocarbon because it does not have hydrogen along with carbon. But if you look carefully, carbon tetrachloride can be derived from methane if these 4 chlorine atoms can be replaced by 4 hydrogen atoms. It can give you methane. So carbon tetrachloride can be derived from a hydrocarbon, namely methane. The 3 important groups of hydrocarbon are alkane, alkene, and alkyne. Alkanes are those hydrocarbons in which there is a carbon-carbon single bond, whereas alkenes are those hydrocarbons where there is one or more than one carbon-carbon double bond, whereas alkynes are those hydrocarbons which has carbon-carbon triple bond. If you look into an alkane where there is a single bond between all the carbons in the chain, you can see that it allows maximum possible number of hydrogen atoms to bind with it or to bond with it. Therefore, it is regarded as a saturated hydrocarbon, whereas alkene and alkyne are regarded as unsaturated hydrocarbons. All the alkanes, all all the members of the alkanes, all the members of the alkenes, all the members of the alkyne follow a general formula. The general formula, GF, that is the general formula of the alkane is CnH2n plus 2. The general formula for the alkene is CnH2n, and for the alkyne it is CnH2n minus 2. Here the term N denotes the number of carbon atoms. Based on the number of carbon atoms, we can name an alkane, we can name an alkene, we can name an alkyne. Let us see how. If the number of carbon atom is 1, the name of the alkane or alkyne starts with meth. If the number of carbon atom is 2, the name of the alkane, alkene and alkyne starts with ith. For carbon number 3, it is prop. For carbon number 4, it is but. Following the general formula of the alkane, alkene and alkyne, we can work out the molecular formula of the members of the alkane series. Let us work out the molecular formula of the first member of the alkane series. Since the number of carbon atom is 1, the molecular formula will be C1H, 2 multiplied by 1 is 2 plus 2, that is 4. Therefore, the molecular formula of the first alkane is CH4. And the structural formula is 1 carbon bonded with 4 hydrogen atoms. Similarly, the molecular formula of the second alkane will be C2H6. For the third alkane will be C3H8. For the fourth alkane will be C4H10. Let us draw the structural formula of the third alkane, that is prop-N. The molecular formula is C3H8. Therefore, C carbon in the long chain bonded with 8 hydrogen atoms. Please remember that carbon's valence is 4. Therefore, its 4 hands must be satisfied. You can see for the first carbon, 1 bond has already been satisfied by the second carbon. Therefore, the other 3 hands need to be satisfied by 3 other hydrogen atoms. For the second one, 2 bonds has already been satisfied, so 2 more bonds have to be satisfied by 2 hydrogen atoms. For the third one, 1 bond satisfied already, 3 more bonds have to be satisfied by 3 hydrogen atoms. The structure of the first alkene. Following the general formula CnH2n, the molecular formula for the first alkene will be C1H, 2 multiplied by 1 is 2, the CH2. If you draw the structure of the first alkene, it has 1 carbon bonded with 2 hydrogen atoms. But as we know that carbon's valence is 4, therefore 4 of its hands must be satisfied. The remaining 2 are not satisfied in this case. Therefore, mid-in is not possible. Let us work out the molecular formula of the second alkene, where the value of N is 2. C2H4 is the molecular formula of the second alkene, and the structure of ith-ene is 2 carbons, and since it is an alkene, there must be a double bond between the 2 carbon. So each carbon has 2 bonds already satisfied, and the remaining 2 has to be satisfied by 2 hydrogen atoms. The molecular formula for the third alkene will be C3H6, and that for the fourth one will be C4H8. Let us work out the molecular formula of the first alkyne. C1H, 2 multiplied by 1 is 2, minus 2 is 0. It is 1 carbon with no bonds with hydrogen. Therefore, this structure is not possible. Let us now work out the molecular formula of the fourth alkyne. The fourth alkyne, the carbon number is 4, and hydrogen number will be 2 multiplied by 4 is 8, minus 2 is 6. The molecular formula of the fourth alkyne is C4H6, and the structure of butene will be 4 carbon in the long chain, 1 triple bond. Will the triple bond be here and satisfy the remaining bonds with hydrogen? So, in this part we have learned how to work out the molecular formula of alkane, alkene and alkynes and draw their structures. Let us just do a short recap on whatever we have learned till now. The three major groups of hydrocarbons are alkanes, alkenes and alkynes. In alkanes, there is a carbon-carbon single bond. Alkenes have carbon-carbon double bond, alkynes have carbon-carbon triple bond. The general formula for alkane is CnH2n plus 2, for alkene it is CnH2n, and for alkynes it is CnH2n minus 2. Following the general formula, we can work out the molecular formula of the alkane, alkene and alkynes, and we can draw their structures. Having learned about the three groups of hydrocarbons, let us move to the next segment where we learn about homologous series. To understand what homologous series is, let us first work out the molecular formula of the first 4 alkanes. The molecular formula of the first alkane is CH4, second one C2H6, third one C3H8, C4H10 is the molecular formula of the fourth alkane. And the names are methane, ethane, propane and butane. If you notice carefully, the 2 consecutive hydrocarbons in the alkane series, they differ by 1 carbon and 2 hydrogen. That is, methane and ethane differ by a CH2 group. Similarly, ethane and propane differ by a CH2 group. Propane and butane also differs by a CH2 group. This is one of the characteristic property of a homologous series, that the members, the 2 consecutive members of the same series will differ by a particular group, which is CH2 in this case. Another important characteristic property of a homologous series is that all the members in the series, they follow the same general formula, which is CnH 2N plus 2 for the alkanes. And all the members in this series, they have carbon-carbon single bond. So what are the three major and important characteristics that we have found out from this alkane series? They are namely that the two consecutive hydrocarbons of the same series, they will differ by a CH2 group. They follow the same general formula and they have the same functional group, which is a carbon-carbon single bond in this case. And as the chain length gets longer, their physical properties, namely the melting point and boiling point, differs. If we look into the first four members of the alkene series, and there is no methene, so we start with ethene, C2H4, C3H6, C4H8, C5H10. These are the first four members of the alkene series. If you look at them, they also, the two consecutive hydrocarbons of the series, they also differ by a CH2 group and follow the same general formula, CnH2n in case of alkene, and have the same functional group of carbon-carbon double bond. And as we move down, the chain length increases, which makes their physical properties, namely their melting point and boiling point, different. So what is a homologous series? How can we define a homologous series? Let us define it like this. A series of hydrocarbons of a particular family or particular series in which two consecutive hydrocarbons differ by a CH2 group in this case and has similar chemical properties but different physical properties. Now, having learned about the homologous series, let us move into the next segment of ours, which is the reactions. Let us study the reactions involving alkanes and alkenes. The three major types of reactions involving alkanes are combustion reaction, substitution reactions, and cracking. What is a substitution? What is a combustion reaction? All alkanes burn in air, that is, they react with oxygen in air to form carbon dioxide and water, and in the process they release out a lot of energy. For example, when methane reacts with oxygen in air, it forms carbon dioxide and water and releases substantial amount of energy. Let us balance the equation. 2 oxygen on this side of the arrow. We put 2 here, it makes 4 oxygen. Let us put 2 here, it makes 2 oxygen here, and 2 oxygen here, makes it 4 on the product side. So 4 oxygen on both the sides of the arrows, 1 carbon atom, 4 hydrogen, 4 hydrogen. Therefore, this equation is balanced. Now we move to substitution reaction. What is a substitution reaction? Substitution reaction is a one in which one atom substitutes for another atom in a molecule. Let us look into this equation in this reaction. Suppose we have an alkane, methane, reacting with a chlorine molecule, which is essentially 2 chlorine atoms. In this reaction, each time one chlorine atom substitutes one hydrogen atom and forms haloalkanes. The hydrogen that was substituted combines with the other chlorine atom, forming HCl. In the presence of excess of chlorine, all of the hydrogen atoms will be substituted by chlorine atoms. In the second phase, the second hydrogen atom can be replaced by another chlorine atom, giving rise to dichloromethane. The first one was monochloromethane, the second one is dichloromethane, along with the release of HCl. In third step, the third hydrogen can be replaced by the third chlorine, forming trichloromethane. Fourth step, the last hydrogen can be replaced by the fourth chlorine, forming carbon tetrachloride. So we have learned about the substitution reaction where an atom substitutes for another atom in a molecule. Now, having learned about the substitution reaction, let us move into cracking. What is cracking? Cracking is the process of breaking down long chains of hydrocarbons into smaller ones. That is, longer hydrocarbons are broken down into smaller or shorter hydrocarbons by heating the longer hydrocarbons in the presence of a catalyst. For example, if hexane is thermally decomposed, it gives you butane plus ethene, which tells us that when a longer hydrocarbon is heated in the presence of a catalyst, the longer chain is broken down into shorter molecules, namely giving butane and ethene in this case. Let us do a short recap on whatever we have learned about the reactions involving alkanes. The three important reactions involving alkanes are combustion reactions, where alkanes burn in air to give you carbon dioxide and water along with the release of energy. The second type of reaction is a substitution reaction, where alkanes react with other atoms and each time hydrogen atoms get substituted by the other atom. And in the presence of the excess of the other reactant, all the hydrogen atoms can be replaced or substituted. The third type of reaction involving alkane is cracking. Cracking is the thermal decomposition of a longer hydrocarbon molecule into a smaller or shorter hydrocarbon. Remember, longer hydrocarbons doesn't have that many uses as the shorter hydrocarbons has. Therefore, breakdown of a longer hydrocarbon by heating the longer hydrocarbon in the presence of a catalyst can give you shorter hydrocarbons. So those were the reactions involving alkanes. Now let us move into the reactions involving alkenes. Among the reactions involving alkenes, in this section we will be learning about the addition reactions. What is an addition reaction? Addition reaction is a reaction in which parts of the reactants are added or combined with the carbons sharing the double bond. For example, now before we move further, let us see what can we add. What can we add? We can add an halogen. We can add halogens like chlorine, bromine. We can also add hydrogen. We can also add water. Let us try to add an halogen to an alkene. Let us start with an alkene named ethene. Eth. The root name eth suggests that there should be 2 carbon atoms. Since it's an alkene, there must be a double bond and the 2 other bonds satisfied by hydrogen atoms. Let us try to add an halogen to an alkene ethene. If you want to add chlorine to ethene, we have to add these 2 chlorine atoms to the 2 carbons that are sharing the double bond, and it will give you a haloalkane, namely dichloroethane. A recap of what we have learned. An addition reaction of an alkene with a halogen always gives you an haloalkane. But this reaction takes place under high temperature, high pressure, and in the presence of a catalyst. Similarly, if you want to add hydrogen to an alkene, we have to add these 2 atoms of hydrogen to the 2 carbon atoms sharing the double bond. Adding hydrogen to an alkene gives you an alkane. In this case, it is ethane produced from ethene. Now let us try to add water to an alkene. Let us take ethene once again and try to add water, which is essentially H and OH. We have to add H and OH to the 2 carbon atoms sharing the double bond, giving rise to this structure. The presence of OH in a carbon chain makes it an alcohol. Therefore, if you add water to an alkene, we get alcohol. The name of the alcohol we have produced is ethanol from ethene. In this section we have learned 3 addition reactions involving halogen and alkene, water and alkene, and hydrogen and alkene. When hydrogen is added to an alkene, it gives you an alkane, whereas when water is added to an alkene, it gives you an alcohol, whereas when you add a halogen to an alkene, it gives you an haloalkane. So we have covered the reactions involving alkenes and alkenes. Thanks for listening to me patiently. In our next video, we'll be learning about isomers and the different types of functional groups that are associated with the carbon chains. Till that time, take care, see you.